show the GitHub page. So I'll assume that's a yes. So I'll assume that you all clone. Oh. So to find the repository, you go to just github.com, then you search for Baremetal emulation without spaces, all lowercase. You should be able to find it. Then within the repository, you can find the slide deck. So this, so you can follow the slide deck on your own machine. So if you can't see clearly on the screen, or if I'm a different page, you can follow on your own computer. And yeah, during the exercise, if you have any question, don't hesitate. Also, the solutions, so how to solve these exercises, are included in both the repository and in the slide deck. So don't hesitate to peek at the solutions. That's perfectly fine. So, all right. So we move on to the theory. Uh, so we'll see CPU architecture. We'll work with three different ones. And the most like important CPU register for our work here. So we'll work with the program counter, which is also called the instruction pointer. So it's a CPU register that contains the address of the next instruction to be executed. And we'll also work with the stack pointer. So we have to set up the stack ourselves or figure out if the stack is properly set up by the code that we try to run. It's not always the case. And then we'll see the reset vector and the tool chain. And finally, the memory map peripheral. So how to access peripheral like communication devices by finding them in memory and reading and writing memory. So about the architecture in this workshop, we'll see three different ones. The first exercise, use ARch64, which is a ARM architecture and 64 bits. So it's a most common one, I think, in IoT devices these days. Although older devices and cheaper devices might use ARM, but 32 bits. They won't always use the 64-bit version of ARM. And at last, there are another architecture called RISC-V, which is like open access. So you can ask a fab to build a RISC-V CPU without having to pay licenses to RISC-V. If you want to build ARM CPU, you'll have to pay license. So some manufacturer will choose RISC-V instead, and it's becoming common with Chinese IoT devices. And it's like devices designed in the US will mostly use ARM. So here's a screen dumps, like 3 dump of registers and instructions for those 3 architectures. So you can look at difference and also similarity. So we can observe that they have like different register names, like the AR64 use X register, ARM use R registers, and RISC-V use like T and A registers. Although in all cases, welcome. In all cases, these 3 architecture, the program counter is called a PC. So there's a PC register, and that's the instruction pointer. On Intel, let's say you have Intel 64-bit, the instruction pointer will be called RIP, but on Arch 64, ARM, and RISC, it's called PC. Same with the stack pointer. Stack pointer is called SP on all these 3 architecture. And also when you can notice that is similar is all instructions are encoded. It's like a single instruction on Arch, AArch64, and ARM are encoded using 32 bits. So let's say you have an instruction at address 0, then the next instruction will be at address 4, then address 8, and so on and so forth. There are like times when the ARM can also be encoded on 16-bit. That's the thumb mode. But in this workshop, we won't see a thumb mode instruction. And RISC-V, it's also encoded using either 32 or 16-bit. Again, there are exceptions to that, but we will see a most like regular instruction size. It's different that Intel, again, Intel use variable instruction size. So I think working in assembly mode on these architecture are easier than the Intel one. All right. So this slide, we covered it already. Any questions so far about registers and CPU architectures? No question? All right. The reset vector. So reset vector, the CPU will go at a specific address once the reset line is activated, and the reset line will activate at power up. So you power up your CPU, will have a like reset interrupt, and we'll go to the reset vector and we'll start running code there. And there is a thing called the C runtime. The C runtime is a things we need to initialize before we can run our C code. So the reset vector at some point will have to call the C runtime to set up the CPU state, namely the stack pointer. And then the C runtime will call our main function we define in our C code. And about the stack pointer, the stack will grow backward. So when you call a function, the stack pointer is subtracted by some amount to make room for a local variable. So we need to set the stack pointer rather high in memory. So we'll load our executable in the lower part of the memory space, and we'll set our stack pointer at the higher part. And it's like if we run out of memory, the two will meet in the middle. That shouldn't happen. But yeah, that's why we need to set the stack pointer higher up. And also one thing that I discovered by making this workshop is, let's say you have a firmware dump, so you desolder a flash chip, you manage to read it, and you're not sure where the code actually start. Where is your entry point? So if you want to find the entry point, you can find the reset vector address in the documentation if it's available, but sometimes it's not. So what you want to find instead is an instruction that will set the stack pointer to an absolute value. So the bootloader to be run, the code that runs before the bootloader will need to set the stack pointer. So you want to search for such an instruction to locate your entry point. All right, about the tool chain. Tool chain, we use like 3 tools of that tool chain. The first is the compiler. So a compiler, you'll have a source file, and it will convert your source file into an object file, which is like executable code that the CPU could run, but it's not in a usable form. It's like it's a part of a puzzle at this point. The assembler will do exactly the same, but for assembly code. So let's say your C runtime needs to be in assembly because you cannot run C at this point. So it needs to set up the machine so your C code can run. So you need a small file with a few assembly instruction that set the stack pointer and then jump to your C code, essentially. In real life, might be more complicated, but in this workshop, it just do that. The linker will take all these object file and will create the executable. And in the linker, we can define a symbol like the address we load our code, and also the address we initialize our stack pointer with. So we might have to change the linker file. Let's say if we want to port our code from one specific machine to another. So what we'll do that in the second exercise. Yeah, that we already covered the C runtimes, like on the operating system. Let's say you want to compile and run a real C file on a operating system. It will also set ARGC and ARGV, so you can consume command line arguments. And if you have like C++, it will invoke the constructor. But in our case, we won't do any of that. We'll just do the first part. Uh, so in the exercise, that C runtime is either called crt.s or boot.s. In real life, they might also have different names, but it's good to look for S file if you have like a source code for embedded device. Um, yeah, that's the call graph. So reset vector calls C runtime, then the C runtime will call our entry point, which is called K main. The peripherals. So if you want, usually if we want to access, let's say a network card, a UART, or any device, we do access it by reading and writing memory at the address our peripheral will be located. So that's the manufacturer who decide like which peripheral is available on this device and where they are located in memory. So we'll learn how to find them. In QEMU, there is a thing called a monitor. So when we run the emulator, the monitor allows us to oversee the emulation and do some operation like dumping the memory or expose GDB. And there is a command called info memory tree, which allows us to display the memory map with all the peripheral and their addresses. So we'll be using the PL011 UART to write Hello World on the screen. So the goal is to write simple program that will write Hello World, and that's the emulated UART that we'll be using. There's another way to figure out the memory map on a device, which is called a flattened device tree blob. That's a data structure that contains all the peripheral on a device and their addresses. And when you work on real hardware, it will be present on the flash. If you have access to a UART on real hardware and you look at the boot messages, you should find, it's like, you might not find it all the time, but you should find the address of that flattened device tree. Then we'll see how to use it to do recon on the machine to have the memory map. And at last, there is an instruction in QEMU that allows to dump it. So you can run QEMU with a specific board and just tell it to dump that flattened device tree on disk so you can inspect it and stop the emulation right there. So that's an example of it's like a flattened device tree. So the STDR UART is specified, so you can see the address. So you can uh, You can set it in your code, or you can access it with the so you can find code that access that address using a disassembler. So you know then the device will communicate with the UART. About QEMU, QEMU can emulate several CPU, several architecture. It can emulate peripheral and also buses. So we'll use it to load the binary. We'll use either the kernel option or the device option to load binaries for emulation. We'll see the difference between the two. And also QEMU can expose a GDB server so we can connect with our GDB client and debug the code that is being emulated. So to run QEMU, you need to install like the QEMU system for all the architecture you want to emulate. So we have like 3 QEMU binaries. We'll actually use 2. The QEMU system ARch64, which can also emulate board with a ARM 32-bit CPU. So we'll do ARM 32-bit emulation, but with the QEMU system ARch64 binary. It supports both version of ARM. And we'll also use the QEMU system RISC-V64 for the RISC-V machine. So if you want to know which board, which machine QEMU system binary supports, you can use the capital M help option, and it will list all the supported machines. All right, the kernel option. When you want to load a binary with QEMU, uh, kernel option will support like a known executable format like ELF. So when we use the linker to create the ELF file, in the ELF file, in the header, we'll have the architecture of the file and the base address. So we'll have data within the ELF file. QEMU will need to load the file in the memory of the emulated machine and start emulation. We can also use the device option. Then we can specify things manually like the load address, and we can tell QEMU, it's like we can tell it where is the reset vector. So we can set the start address of the emulation. That we already cover. Yeah, there is a case. It's like if you attempt to use the kernel or device option to set the start address, some machine that QEMU support will have like hard-coded reset vector, so it won't obey you. So if you set start at this address, like 0x8 then 70, we use that particular address in the workshop, and you attach a debugger and you look at the instruction pointer where the debugger starts, it won't be there. It will be at the address of the, what do you call that, the zeroth stage bootloader in RISC-V. So the reset vector in this case is hard coded. You cannot change it. You cannot set it. So it will run its own code, then eventually branch to the code that you want to emulate. Same with, we already covered the device option. About the device option, it does support known executable format like ELF, but it does also support the raw binary code. So let's say you really want to emulate shellcode, then you can load it with the device option. And I think by default it will support raw file, but you can specify that there's a raw executable code, and then you can emulate your shellcode. All right. So at this point, everyone should have the Jupyter notebook environment running. So I'll walk around to make sure people are ready for the first exercise. If you don't have the Docker container built, I have two USB keys with the already built container. So that can speed things up. So let me unmount this. And all right. That's the wrong workshop. Ok, ça, regarde, c'est ouais. Ouais, je pense envoyer le lien vers le workshop de l'année passée dans le store. All right. So, most of you have access to the Jupyter notebook. So you should see this. We can dismiss the dialog here. In the Jupyter notebook, there is the launcher, and from the launcher, what you want to use is the terminal. So we won't be using the Python kernel. I just want to use the Jupyter notebook for this web shell, which I like. Um, so we'll do the first exercise. The first exercise is like really simple, should work out of the box. So you have like a run.sh script and the debug.sh, and we also you also have the source code. So the boot.s I told you about is the C runtime. The kernel.c file is really the our C code, and the linker.ld is the linker script. So it will tell the linker what to do and how to create the executable file from the object file. And the executable file that is created is called kernel.elf. So yeah. Uh, all right. So if we look at the run.sh script, let's see it called QEMU system AR64. It will use the vert board. So it's a artificial board. It doesn't really exist. It's just a board that is being created by the QEMU developer to play with the emulator. So it's a virtual board. And the CPU on that virtual board is ARM Cortex A57, which is really ARM 64-bit CPU. And it runs with those options. So it uses the kernel option to load and emulate our kernel.elf file. And I added a few options like to disable the audio device because uh, in some case, I forgot to add the dash audio none option, so you'll see ASA errors. You can dismiss the ASA errors. You can ignore them. They're harmless. And also, I use the dash no graphic option to disable the GUI, so we'll have like only the text, the serial terminal. So if we run the run.sh script, you should have like that result. You should see hello world being printed on screen. And then after it ran our main function, it will enter infinite loop. So it will just hang there. So if you want to stop the emulation, you can use Control A and then X, and you should have like the QEMU terminated message, and then that's it. If we want to look at the source code first, we need to look at the make file. So we'll see the tool chain being used. First, the assembler will take boot.s, compile it. So that's our assembly file, our C runtime. So we'll assemble it into boot.o, which is a compile object file. So that's our executable code for our C runtime. And then the compiler will do the same, but with the kernel.c, so it's really C code, and create the kernel.o object file. The linker will use the linker script linker.ld to create the executable from the object files. So next thing we look at is the linker.ld. So it defines the base address. So our text section will be loaded at that address in the emulated machine. And it will start with the boot.o. So the first thing that we want to run is our C runtime. So that address become our reset vector, and the reset vector will run the code in boot.o. from the boot.s file, and then it will run the other object files. So the kernel.c. So there is instruction in the boot.o that will jump to our main function in the kernel.o object file. So creates the text section from the two object files, but boot.o goes first. And then it sets the stack pointer so that it will allocate 4 kilobyte of memory, then set the stack pointer. So it's not really at the top of the memory space, but it's only like 4 kilobyte over the text section, but it's plenty to write hello world. We won't need that much stack. About the boot.s file, so it uses the stacked up symbol from the linker script. So here's where the stacked up is being defined, and then is being consumed in the boot.s file to set x30 register. Then the x30 register will be copied into the stack pointer. Why they don't like just copy it in the stack pointer, I don't know. So it's like I didn't write that. It's an example hello world code that I found on GitHub. It's like I just use already written example. And then here it branch to our kmain function, which is defined in the kernel.c file, and then it goes into infinite loop. So if we look at the kernel.c, kernel.c, first thing, there's a UART pointer being defined, and it defined the UART pointer at that address. So that's our memory map UART. And if we know, if we want to know how to find that address, there's the QEMU monitor I told you about. So we can do a simple experiment here. We can use the debug.sh. We can look at it first. So the debug.sh had a few options to the QEMU emulator. It will have the lowercase s and the capital case S. Lowercase s means expose a GDB server and expose it on port 1234. If you want to use a different port, then you replace the lowercase s option by lowercase GDB, then TCP, colon, and then the port. It's in the slide deck if you search for GDB. Yeah. So slide 29, you have the GDB option that you could use if you want to expose the GDB server on a different port than 1234. But by default, it's 1234. So I need to go back. Yeah. So let's run the debug.sh. So the capital S option means that we want to it's like stop the emulation and wait for the debugger to connect and to allow the execution to proceed. So it will wait for us. And then we use another launcher. And the monitor, there is an option to tell the monitor to listen to port 55555. So there, 55. So if we want to access it, we can use telnet, localhost, and then 55s. And you should have that QEMU prompt. If you type help, you have a whole bunch of options, but we will only use two in the workshop. The first one that we will be using is info M3, and that's our memory map. And if we look for our UART in the memory map, we find it at 9, then 6 zeros. So 0x9000000. And we saw that address in our kernel.c file. So let's say want to port code to a different machine. Then on that different machine, UART may not be at the same address, so we might have to look at the memory map again and update this. And yeah, the rest of the code is pretty self-explanatory. So it will, the K-main will call the print function with hello world, and the print function will iterate over each of the character and then call the putchar function. And the putchar function really takes the character and write it at that memory address. And our PL011 UART is designed in such a way that if you write something at the base address, that's the transmit buffer. So it will take it and send it. Other UART might be different. So you might have to set register by writing other part of the memory because it's not like it's a memory space. So the UART will occupy some amount of memory starting at that address. And in some case, it has like register. So if you want to configure it, you have to write into specific memory cells to configure your UART. And also the receive buffer will be at like different address. So to figure that out, you need to look at the technical documentation of the peripheral. What you'll be doing then is really writing a driver. Now, don't have to write much of a driver. We just write a character at the base address and it works. So, any question about exercise 1? Yes. Uh, we don't see it in GDB. We see it in the QEMU monitor. So if I load the monitor again, you need to run debug.sh. So that will expose the QEMU monitor. And then you use telnet localhost, then 5555, so 55555 to connect to the monitor. Then from the monitor, the command to display the memory map is info m3 or info memory tree. Yes, the question. Yeah. 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 Probably write 0 after. I'm not entirely sure because to figure that out, we'll need to look in the that particular peripheral and QEMU source code. But yeah, probably it writes a character, then writes 0 in that address. But yeah, good point. Uh, any other question about exercise 1? All right, we move then to, I need to power my laptop, sorry. I'm about to run out of battery. Euh, Ça, puis je peux utiliser celle-là si tu t'approches à ça. Là. Ouais. De toute façon, il n'y a pas beaucoup de circulation de ça. Bon, toi puis moi, personne va le faire. Et là, parce que je m'en ai manqué de courant. Ça a arrêté. Fun. All right. Now we have juice, so we can go on. Um, so after you use the info-m3 command, you can leave the QEMU monitor with the quit command. If you use the quit command in the QEMU monitor, that will terminate emulation. So you see debug sh is running. If I use quit here, my debug.sh will exit. So that's one way to exit the emulator. Now we move on to exercise 2. Exercise 2 is the exact same code, but our goal here is to run it on a different machine. So you can compare debug.sh and run.sh with exercise 1 and exercise 2. What you'll notice, the differences, two major difference. We no longer use the vert board. We use a different board, the V Express A9, and the CPU on that board is the Cortex A9. And if you look, if you search Google Cortex A9, you'll notice that it's a 32-bit CPU. So different board and different architecture. If you look at the files in the ext2 folder, you'll see kernel.elf file, the compile file by default. It's the same one that we use in exercise 1. So it's AR64 code. So if we try to run it, of course, it will immediately fail. If you try to run debug.sh, it won't even like stop for debugger. It will notice that it's the wrong architecture and it will immediately exit. So if you try to run debug.sh and it returns immediately, it means that you have to rebuild the code for the proper architecture. So if we look at the make file, you'll notice I did make the challenge slightly easier by using the proper toolchain executable. Since we want to build and run ARM 32-bit code, then we need to use ARM 32-bit toolchain instead of the 64-bit one. And we'll build the executable the exact same way. So we build a C runtime, we compile the kernel.c into kernel object file, then we assemble the two using the linker. So if we try that, you should get that error message. What is that error message? That's your first challenge. So anyone here want to try and see what could be wrong here? Yeah, exactly. So the X register, as we saw on the screenshot, yeah. So X register are AR64 registers. So on ARM 32-bit, we use R registers. So the boot.s file needs to be modified with we need to use ARM 32-bit register name here. So the LDR instruction is the same, so we don't need to change that, but that we need to change. Any suggestion about which register we should use on ARM? Yeah, it's like R, but there is a specific register on ARM, which is the frame pointer register. It has two names. It is simply called FP, so that will work if we replace X30 by FP. Or there is also another name, which is R11. So if you use R11, then you'll be setting the frame pointer with the stacked up symbol. And then once you set the frame pointer, then you can set the stack pointer at the same place. So we're ready to start running code. So if you try that, you use Control S to save your boot.s file, then R14? Okay, let's try and search. Whoa, just want to make sure. Yeah, FP works. R14, ARM32. Just want to correct myself. And yeah. No, R14 is the link register. Yeah. Well, we'll look at it after the workshop. So you can use ARM11, you can use simply FP, and it should work. So if we go back to Jupyter, we save this file, then we run make again. Oops. I saved the wrong boot. Make sure when you modify the boot.s file, make sure you are the exercise 2 folder. Always make the same mistake. So I'm editing the wrong file. Uh, so we go in exercise 2 folder, and then you replace this FP, save, then make again. And if you replace the register properly, your make command should succeed. So then you'll have a ELF file that is really ARM 32-bit code, and then you could use run.sh. But if you run the program, then nothing happened. There is no hello world that shows up on screen. So we need then to figure out why. So I'll walk you through the debugging process because it's a bit hard to do it in the time frame that we have. So I'll show you. So first we need to run debug.sh to expose the debugger, and we'll then use the debugger. So I need a new terminal here. So the debugger is called GDB multi-arch. Who here is familiar with GDB? So part of the room. So the rest of the room is not that familiar with GDB. So we'll do it like step by step. Uh, so first you invoke GDB multi-arch and then our executable file as argument. So it will load symbols from kernel.elf, and our file is not stripped. That means that our function name are available in the file and will show in the debugger. So that helps us a bit. So you should see a pound GDB prompt. Pound GDB is a add-on to help in the reverse engineering with GDB. We'll see like each time there is a breakpoint that is encountered, or if you go to instructions step by step, it will show a state of the CPU at each step. And then there's a few command that we need to set. The first command is to tell GDB and pound DBG to show us like reduce register set. We don't want to see all the register. There is a lot of them that we don't use. We don't care at all in this workshop. So we care about a few first data register. Let's say for ARM32, it's like R0, R1, R2, and so on. And the stack pointer and the program counter. We can ignore the rest of the register. So we use the set show compact reg on. So that tells pound dbg when it shows up the machine state to use to show only a few of the register, not all of it. And then if we want to connect to our QEMU expose debugger, we need to use the target command in GDB. I use extended remote. If you use simply remote, I think it will work the same way. It's like extended should have a few more function, but we don't really use them. I'm just used to use the extended remote uh, argument, but you could just use target remote. And then the QEMU expose debugger will be listening on localhost port 1234. So we need to give the debugger that address so it can connect. And if you run that, you should have that screen. So I'll work around to make sure like most of you, if not all of you, uh, do have that screen. So you should see the program counter loaded at our address. If you remember that address, it is set in the linker script. So linker script set the base address, and on this machine, that base address will become the reset vector. So our execution will start there. Uh, so we know we see also the symbol underscore start, which is also set in the linker script. And we see our stack pointer being set, and then there's a branch to our k-main function. So make sure everyone do have that. You're welcome. So, uh, you should all, you should all have like this screen. So from here, um, is there any question? Like, can we proceed? Yeah. Pound 8 here. Should be like something like PC, whatever's in PC, -8 or +8. I'll search it, but should be something like that to access like 8 byte above or below. Then load into FP. You can try and look at the FP register and the PC register to see how the register are modified when you run that instruction. So we'll do it right now. We'll start running code. What we want to do here is to figure out why our hello world string is not getting printed on that board. So we'll run code until we reach, so we use the SI command, which is like step instruction. So you're telling GDB to run an instruction and stop immediately after. So we can look at our register being modified, and we want to run code until we'll reach a specific address, which is this one. So you use the SI instruction and you step until you reach the address 40100058. What is so special about that instruction? There's a store instruction, and then we see the pound -8. So in this case, it wants to take the data that is in R0. So if we want to see what's in the R0 register, we can use the info register R0. So in the R0 register, we see what looks like a memory address. So if we want to see the data that is at that specific memory address, we can use the examine command in GDB. So the examine command is hex, then we use a space, then we give it argument, which is like slash x, oh, 10, it's 10xb. Yeah, oops. Right? Yeah, sorry. Use then we have to specify the memory address we want to read. So we can copy the number or just use the $sign R0. So if we use the examine, then slash 10xb, slash 10xb means that we want to read 10. The B means bytes. So we could replace it, let's say, by double W, and then that will be like words. So we want to read bytes and display them in hexadecimal. So we can recognize what looks like ASCII here. So if we want to sit as a string instead, we can use x/s, and we see our hello world string. So our R0 register really contains the address of our hello world string. And the store instruction wants to write that at a memory location pointed by FP, the FP register -8. So we can also display the memory location pointed by FP -8 the exact same way. So we do FP -8 as the address, and we'll see all 0. That is because we did not run the instruction yet. So the instruction pointer, the PC point at that instruction. So if we use the SI command again, then the instruction will be executed and the pointer will go forward to the next instruction. So the result should be that whatever is in R0 will be copied at FP -8. So let's try it. So I run the store instruction. It does run. And then it will go, the next instruction is the branch one. So let's look at FP -8 again. If we use the examine command, still zeros. Why? Any idea why the memory has not been written to? Anyone? All right. So seems that the memory may not be writable because our store instruction just failed. It failed to write data in memory. So we have to figure out why. So in this case, we'll look back at the memory map like we did at the first exercise. So leave the debugger there. Don't close the debugger just yet. And we have the debug.sh running. We leave it running, obviously. If we look at the debug.sh script, we have our monitor that is also being exposed on the same port that we use in exercise 1. So we'll connect using the monitor. So we open another tab, then another web shell. And then from the web shell, we use the telnet localhost, and then 5.5s. So we are on the QEMU monitor, and we run the info mmemory3 command again. And what do we notice here? And is the memory address we did load our code to is marked as ROM. So it's read-only memory. Because remember, we're not running on the same board, we're not running on the same architecture, so the memory layout is different. So if we want to port code from one machine to another, then we need to see the difference in the memory layout in both machines. So obviously we want a read and writable section of the memory to load our code. So I suggest we use this one. We could also use this one, the high memory, but I will use this one. So it's SRAM and it's RAM, so I will expect the code to be able to write to it. So the address is 48, then 60. So what is the file which set the memory address where we load our code? Do anyone remember which file I should edit to change the memory address where our executable is getting loaded by the emulator? Yeah, linker. So we just do a bit of copy paste here. So since we know that we have to change the linker script and recompile the program, then we can leave the monitor and the debugger, and we can leave also debug.sh. So if you do quit in the debugger, that should terminate emulation and debug.sh will return. So then we can edit the linker script. And we replace that address here by 48, then 60. And we use Control S to save. And we don't need to change anything else in the linker script. So since we changed the linker script, we need to run make again to rebuild the executable. And once we did that, we'll redo the exact same step in the debugger. So we start debug.sh again. So we'll wait for our debugger. Then we run the GDB multi-arch with kernel.elf as argument again. And if you use the arrow, like the up arrow and down arrow, you should be able to it's like repeat your command you type earlier. It's like GDB does have a history, so it writes to an history file. So if you run GDB again, then you're getting your history just like bash history. So we set the compact register, then we use the target command again. Good. Recover the target command. And when you use the target extended remote and you establish the connection with the GDB server and QEMU, you should notice that the start address, the program counter address is now 48 with 60. So the new executable has been updated with our new memory address we want to run our code at. But it's the same program. So if we use the SI instruction and we start running code, eventually we'll reach, where am I? Yeah, am I in the right place? So we should have, instead of 40100058, then it will be like 48000058. So that's our same store instruction that we will look at the memory being written to see if it works now. So before we run the instruction, we will check the content of fp -8 again. So I use the x/10xb, then fp -8. It's all 0, fine. We did not run the store instruction yet. But if we use step instruction again, then we execute the store instruction. So if we display memory. Now we could see that the write was successful. So you should see the content if we do info registers R0, should see 480000 C4, and we should see that at FP minus 8. If we use the x/1xw, so display one word at that memory location, we should see the same content that is from our R0 register. So we can see that now the memory is writable and our store instruction succeeded. But if we use them continue, still no hello world. Any idea why? Yes. You mean the PL0? Yeah, not the same address. So yeah, what he said is our serial port, our peripheral, is also at different memory location. So the memory location we try to write to in kernel.c, which is this one, which worked in our vert machine, now doesn't work in our Express V9 machine. So if we go back to our memory map, so we access the monitor again and we run the info m3 command. We see our first PL011. It is at the memory location at 10.0.0.9 10.0.0.90.00. So different memory location, and we'll see in the memory map, I think the address we set, like the address from the first exercise, is not even valid memory in the second machine. So it's like our character are not going anywhere. So we need to update that with that address. So just copy, then paste in kernel.c. Save kernel.c. And since we modified the code, we need to run make again. So now, yes. Yeah, I choose the first one. It's like from the flattened device tree, if we try to dump the flattened device tree, it might be marked as the serial port that has to be used for standard output. That's one way to find it. Otherwise, it might be the first one that is the one that we want. It might not be. If it doesn't work, then you can try the other ones. But also, if you have access to like manufacturer provided code, you can figure out like if you can debug or do static analysis, you can figure out the address of the serial port being used if there are several serial ports on the machine. And that's usually the case. It's like manufacturer do like to include like more than one. Any other questions? All right. So we rebuild everything. If we use run.sh again, then you should see hello world. So that's what we needed to change. We needed to change the base address and the UART address so our code could run on a different machine. So now there are two other exercises, but only half an hour left. So that was expected. You have to go over 15 minutes. All right. But what I will suggest is that we skip exercise 3, then go directly to exercise 4, and treat exercise 3 as a bonus. So when we complete exercise 4, if there's time left, we'll try to start exercise 3. Otherwise, I will suggest you do exercise 3 on your own. Uh, it's like whenever you have time to do it. And I'll be available if you have any question later, and I'll happy do it again if you want to do it again, like this afternoon or tomorrow. All right, so let's terminate the emulation for exercise 2 and go over exercise 4. If we uh, go back to the slide deck, um, yeah, go over to exercise 4. Exercise 4 is actually a capture a flag challenge. You might see a capture a flag challenge like that in the competition. I don't know. I'm not a challenge designer. I still compete. Well, I'd like to see something like that. So the challenge here is like some manufacturer doesn't want you to see what is happening on your own devices. So they will resort to obfuscation technique, and some may even encrypt their firmware. But you want to access firmware to assess the safety of a device. So you need, in some case, to be able to break firmware encryption. Yeah, there's many ways to implement firmware encryption. Some are better than the others. Some will use vaults like trusted execution environments. Some will use like trusted platform modules and things like that. But some other, eh, they will just use hard-coded key in the bootloader code. Yeah. So that will be our case. So what we'll need to do here is to use tool for static analysis. I do recommend Ghidra. It's free and it's good enough for my use cases. So I like to play with it. And we'll do static analysis on the kernel.elf in exercise 4. Um, and what we want to know is there any point in time where we could access the plain text firmware from the memory? So another way to break firmware encryption will be to access the key. But sometimes it's easier just to access the plain text. And then how do we extract such plain text if we can access it? So let's try and start our static analysis tool. Uh, so do you have all like Ghidra installed? Uh, I'll take that as a yes. Ah, you do not? Uh, do you know where to find it? Okay. Let's say you want to find Ghidra. You go back on, you can use, whoops. You can just use like a different search engine to search GitHub, because GitHub is getting really picky, and you might experience 429 response when you use GitHub search engine, because like they don't like people to use their search engine too much. So we use another search engine to search GitHub. So we search GitHub, Ghidra, releases. So I use the DuckDuckGo search engine, and will come with the first link will work. So you want the like the National Security Agency version, because some people did like cyber squat Ghidra, so they open different repository with like strange name like government, and they have like they publish their own version of Ghidra, so I cannot assess the safety of such a Ghidra version. So you want to use the real one. The real one is National Security Agency one. Uh, and go to that page. It should have like a zip file. So basically, you download the zip file, you unzip it, and then you run the Ghidra run command from it. Uh, there's a bash, it's like a command Windows command line script and a bash script under Linux that will start Ghidra. But the problem is if you didn't run Ghidra before, Ghidra requires a Java virtual machine, and it does require at least, I think it's Java version 21. So this Java version you can find on the OpenGDK website. And it's the same thing. It's a zip file that you have to download and uncompress. You want to go to the GDK general release, and you click on GDK version 24, and you pick the one for the operating system you're currently using, so the Linux or Windows or Mac one. Then you install OpenGDK, and then you unzip and run Ghidra. And if all goes well, you should have like that screen, but you won't have the project already open. So it you'll have like that screen. So first in Ghidra, we need to create a project. So use the file, then new project, and you let it you let the non-share project option tick. So don't tick share project, pick non-share project, then hit next. Then you choose a folder on your machine you want the project to be located. So I could put it in the workshop 2025 folder. And then you give it a name. So let's say exercise 4, X4. So we'll create a project. Then we need to import the executable file we want to do static analysis on. So to do that, we go back into the file menu, then choose import file. And then we pick the kernel.elf from the repository, the Baremetal emulation repository, and the exercise 4 folder. You pick the kernel.elf and select import. And here we'll ask you to confirm the executable file format and architecture and everything. You don't need to change any of that, so just click OK on that screen. Then we'll start to process the ELF file, and then we'll show it's like the load address and the C file that were used to create the executable file. I did not strip the executable to make the analysis easier, so we can actually do it within the workshop time frame. So just click OK on that window. And then you can double click the kernel.elf file to start the code browser. So it will open the code browser. So the dragon will eat all the byte. All right, code browser is opening. My machine is a bit slow. Yeah. So it will ask if you want to analyze the file. Most of the time, we actually want to analyze it. So you click yes on that, should we analyze the file question. So And then we'll present with a dialog to pick the analysis option. You keep all the default, you don't change anything, and you just click analyze. And the analysis, since it's a really small program, the analysis should be pretty fast. So you see it in the bottom of the screen, and in like 10 seconds, the analysis should be complete. We want actually the function window. So we might click window, then function. And here we'll see all the function names. So that's a bootloader that is not complete. I created it using a code that I could pick up with a permissive license. So I pick up like implementation of a cryptographic function. Uh, if you go in the solution folder in the repository, you'll see the actual source code. So if you want to look at how I did create this thing, you have the source code. Um, so what we want to do here is go from our entry point, and you see our entry point set the stack pointer, and then branch to main function just like we did before. It's the same C runtime. So we click kmain, and then there's a decompile panel. So we could see the decompile code. And from here, we want to figure out what's going on a bit. So we'll see like message being print, workshop 2025, really secure boot firmware, blah, blah, blah. And then we see like SHA-256, and the output of SHA-256 is being fed into AES as a key. So what it really does, it takes some part of the memory which is consistent across boot and specific to that particular machine to create a key. So let's say I want to implement some kind of digital right management scheme where I want my code to only run on my hardware. Then that's one way I could do it. It's like in real life, it's even more complicated, but in this CTF challenge, I just read some byte from the memory at a memory address where I know that these bytes will be set this way only on this board. I checksum that, and my checksum is being used as a key to decrypt the firmware. And then we have like the ES decrypt function, which take a few arguments. So there's local 10, which look like a memory address. And it's like, then we need to figure out the, it's like input and output. So let's say we have that memory address, then local 28, it's not a valid address in our machine. So it might be something different, like the size of the data that needs to be processed by the AES decrypt function. And then local 14, different memory address. So one way to figure out what is the source and what is the destination is to go into that function and figure out like where from where the data is being read and to where the data will be written to. Or another way to do it will be actually run uh, the program. So go in exercise 4, and we run the debug.sh. Yeah, so these as errors because I didn't use the dash audio none option, and so it gives error about sound card. You can safely ignore these messages. And then, sorry. debugger is running, we'll access the QEMU monitor to get the memory map. So we can, from the memory map, figure out which address might be the source and which address might be the destination. So use telnet localhost 55 and info M3. So it's really the same machine that we use in exercise 2. So it's the VExpress machine. So we see from the static analysis that that address is being used, and from the memory map, we see it's again the same read-only memory space. So I think we can agree that this particular address cannot be written to. So that might be the source address, so the ciphertext. And there's a third way we can also figure what is the source, what is the ciphertext, and where will be the plain text. We look at the second number from our decompiler. It's 6 with 7 zeros. And that address is VExpress high memory. And that memory is readable and writable. So that might be our destination. One other thing that we could do is look at the QEMU script. Let's say the debug.sh. We see, oh no, it's used the kernel.elf option. So in some case, I'm not in the right folder. Sorry. Yeah. If we look at the run.sh script, we see the device option being used in QEMU. The device option can load like any file at any memory address, and it won't be necessarily executable code. So we can load data as well into our machine memory, and we can see rootfs.enc. That could be our ciphertext. And we can see it being loaded at address 4 and 7 zeros. So that'll be our source. Then back into our code here. Then we'll assume then that this address is the destination address. So the AES decrypt CBC function will take data from sorry, wrong window, from here and decrypt it, then load it here. So we look at the memory map, it makes sense. QEMU options, like the configuration of the machine, it also makes sense. So how could we verify it? Is once the decrypt function, AES decrypt function is over, it will print it will print a few string. It will print like loading system, license check failed, and shutting down. And there is a memset. So if you wait too long in the process to stop, so try to put a breakpoint and stop execution, our destination memory will actually be erased. So that is to show that sometime on some machine, it could be like a race condition. So you have like a window of time you can access the plain text. So plain text might be available in memory, but only for a small amount of time. So it can either be fast enough or use a debugger or some other way to stop execution before the memory gets overridden. So what we'll do here is we'll note that the address of the print function, so it's 48006000. We'll keep that in our memory, and we'll stop the execution there, then try to extract the plain text, the plain text root file system. So how do we do that? We go back. So make sure you are in exercise 4 folder. So yeah, you're not still in exercise 2. And then it's like if we try run.sh first, you see that the decryption actually takes time. It's like the emulation takes time uh, to decrypt all the root file system. So it should be done in like 30 seconds. So we'll run it. We'll wait. Uh, so when we'll use the debugger, then we'll expect some amount of time to elapse before our breakpoint is actually triggered. So when the program completes, it will say shutting down. And when shutting down is print, then our plain text is overwritten and lost. So we leave emulation. In this case, if Control A, then X doesn't quit the emulator, you can simply try Control and C. So to stop emulation if the first method doesn't work. Then we run debug.sh again. I'll close a few tabs. This we don't need. Right. So the GDB multi. We use GDB the same way. So again, we set show compat reg, and target extended remote. So just like we did in exercise 2, we connect to the debugger. Then we need to set a breakpoint. So our breakpoint needs to be set like right after the decryption happened. So we'll set it at address 48006000. So to set a breakpoint in GDB, we use the break command. Then we have to use star, and we write the address using the 0x prefix. So it's 48006000. So it should respond with breakpoint 1 at, and then it uh, echo back the address. So now we want to tell GB to run code until the breakpoint is being reached. So we use the continue command or just the C command, but we can actually type continue. Enter. So it should take like 30 seconds for the decryption to take place. And then once the AES decrypt CBC returns, our breakpoint should trigger. And that will allows us to access the plain text as we stop execution so that our memory cannot be overwritten since we stop the program. So is that clear? Any questions so far? All right. Um, so then we reach our breakpoint. So we are back to pondbg prompt. And then we have a few ways to dump the memory. There is, I think, in GDB, it's called dump memory. So if we use GDB, that's how we could do it. So we need dump memory. Then we need to specify a file. So it will open a local file using that file name you provide. Then write content from a start address that you specify, unleash until it reaches a stop address that you also specify. But I like to use QEMU monitor better. So if we use QEMU monitor to dump the memory, and we use telnet again, telnet localhost, and then all fives. And then in QEMU monitor, there is a memsave command. So if we do help memsave, that's how we use it. We use memsave, and then the address from our static analysis, we can use copy paste. So we copy and paste. And then the size, and yeah, it's like we're skipping step here, because in real life, you'll have to study the program a bit more to make sure this is the size. So uh, I just tell you it's like this is the size that being used for the decryption. So we need to specify it to dump like all the plain text. And then we specify a file, let's call it like root fs.bin. Let's, and then you should see on the left our root fs.bin being created. So that's the case. Once it's done, then you don't need the program to be running anymore. So you can use the quit command from the monitor. That will stop the emulation. Yeah, and you can leave the debugger as well. So from now, we'll work on the file that we just extract, which is the same size that the encrypted file. If we do a file on rootfs.enc, it's like file doesn't recognize it. It's ciphertext. If we use the file command again, but on rootfs.bin, and it works. And if you see squash file system like this, it means that really you access the plain text firmware. Uh, there is also another command which is useful to scan a firmware file, which is called binwalk. So we could run binwalk on our root fs.bin file. Will take a bit, but again, it does find the squashfs file system, which is a popular kind of file system with IoT devices. Uh, it's not the only one, but it's one that you will encounter quite often. So to process it, um, there's a package called squashfs tool that is installed in the Docker container. And from squashfs tool, there's the unsquashfs utility. So you run unsquashfs against the plaintext file system. So the root fs.bin file. Should see that. And that's when I do a reverse firmware, it's pretty good moment. The moment I can see I did access the file system. In some cases, like that's the hardest part. And then like bugs start popping. So look at our file system. You should see it. It should create a squashfs root folder. So it and then it decompress all the files. So we can see I create a real file system from the I use build tools to create a file system for embedded device. So we can really see, well, we should see files. Let's try has been, yeah. We see files, a real file system, and you could go around and see like the password file. But what we want to do here is to find the flag. So, but in real case, you'll have like all sort of interesting data from the root file system, and then you can really start your assessment to tell if the device is safe or not to use. So if we go in the root folder, then we have our flag. So that's of the CTF challenge. Any question about that challenge? So could you reproduce it? Yes. Yeah, yeah. So it takes longer. Oh, about strip binaries. I have some tricks to give to you. In Ghidra, there is a thing, uh, like I would save. There is a tool, this tool, the version tracking. So let's say in real life, I did several times. I have a bootloader. So I dump a firmware, I dump a flash chip, I have a bootloader, and strings works great to do some recon. So I use strings against the dump to figure out what kind of bootloader. And often it is U-boot being used. U-boot is popular bootloader, and I can also find the version of U-boot. So I know that the manufacturer use U-boot and version blah blah blah. So I'll go on GitHub, or it's not GitHub, but they use a Git repository. So I do check out the exact same version, and I do build U-boot myself with debug symbol. Then I can use the version tracking from Ghidra to compare every single function from the binary that is stripped, which I extract, and the U-boot that I've built myself without the symbol. And this tool is designed to find not only identical function, but similar one, and it uses a bunch of algorithm to compute the similarity. And then I can match function names that I know that I have the symbol with functions in the binary. Work wonders. So that's how you can reverse U-boot with strip symbols. And it will work with other code. It's like the idea is if you have the source for that program, let's say you are facing like OpenSSL library that is statically built, you can also do the same. So manufacturer, well, it's like they will use a lot of open source code. So you can use that, and from there you go to the parent function and the child function. So you can reverse function that are written by the manufacturer within U-boot. And then you can find what I call like the secure boot code. It's like the code responsible to check integrity and sometime decrypt. It's like, and you can find vulnerabilities. So you're really attacking from the flash. So you control the flash data at this point, and so you can, from the flash, fuzz the code responsible for the integrity control that is written by the manufacturer. And yeah, if you can have RC, then you can bypass the checks. So yeah, that completes. Yeah, another. Yeah, it won't really boot. It's like the bootloader that I've made is not complete. So I'm not attempting to load a kernel. It's like if I did wrote a complete bootloader, you could actually run the machine, but I didn't. I did not wrote a complete bootloader. Uh yeah, if oh, okay, just make sure if let's say you're here. Okay, so you try here to replace, yeah, but remember what the code is actually doing. If we open kernel.elf again, I'll tell you what is happening and why it won't work. No, it won't change the key because the hash, it's like it takes some byte from the memory of the machine. But what you're really doing here is you change what's in the source address. So there used to be plain text, ciphertext. So you decided that you load the plain text in there instead of the ciphertext. So it will try to decrypt. So it will apply AES decrypt on the plain text. So the result will be unusable. Any other questions? Yes. You mean these numbers? It's the memory map. So in any case, you always want the memory map of the machine. So to get the memory map in the QEMU emulator, you use the monitor. So you start QEMU with the monitor activated, and then you use telnet. Local, yeah. And Guidra, it's like you load the kernel.elf in Guidra, and it will use information that is within the header of the ELF file to probably, yeah, that is the memory layout, is the chip, the memory dim icon. And then you'll see the start address. So Ghidra use ELF header to properly display the addresses. And you might also want to change it because in some cases, when you extract a bootloader, you won't have a ELF file. You'll have like just a blob. So you need to figure out the start address yourself. And then I suggest you search in the instruction, an instruction that set the stack pointer to an absolute value that have to be close to the entry point. So then from there, you'll have an idea where to load your code in Ghidra. Any other questions? Yeah, but thank you. Thank you very much. Merci. All right. Stop sharing.